Hello and welcome to this introduction to the UKMARSBOT. I'm Ian Butterworth. I'm currently the chairman of the UK Micromouse and Robotics Society, and I've built a UKMARSBOT so I can give a few tips on its construction. This presentation is for people that have decided to build a UKMARSBOT and anyone who is interested in finding out more about the UKMARSBOT and may then want to go on to build one. First, a few thank yous. The UKMARSBOT is a result of the contribution of many people, and I would like to thank everybody that's been involved, the UKMARS members that have helped, and in particular, Peter Harrison, who did the brunt of the design work and also drawing up the boards for the first release, David Hannaford for initial concept ideas, circuit ideas and designs, and also an excellent build guide that's available to everybody. Rob Probin for his help in the early concepts and design ideas and also providing circuits. Gary, Duncan and Derek for reviewing the circuits and the designs and coming up with improvements. Thank you to everybody. So what will we cover today? I'll talk very briefly about UKMARS and who we are, then get straight into UKMARSBOT, what we set about to do, what was the purpose and the goals, and then on to what we came up with, both for hardware and for software. I'll also show you some of the resources that will help you get started, and then some thoughts that I have had as I've gone through my build about hardware, what do I need to be thinking about, and the same thing for software. Finally, we'll look at whether it works. It does. And then we'll look back at the resources that are available to you to get started on this robot. So who are UKMARS? It's the UK Micromouse and Robotics Society. Micromouse is a very specific competition for robots involving solving mazes, but we're a much wider interest in terms of other robotics challenges as well. We build autonomous robots for fun, and we provide resources for other people so they can also build robots. We run competitions and contests. So 2019, the contest was in BCU, Birmingham City University. In 2021, the international contest will be held in Coventry. In 2020, like many other people, our events were severely disrupted by COVID-19, but we are planning Minos conference for 2021 in June and also the autumn contest in Hazelmere. But we have been successful in bringing about a virtual line follower contest. We send a course around by post and people submit their entries by video. And you can see these on our website and see how people are getting on with that. UKMARS is open for anyone to join, so you might want to think about that. And one of the things that we have come up with is the subject of today's talk, which is UKMARSBOT, a multi-purpose robot platform really suitable for first-time builders. So without any more ado, let's start to look at UKMARSBOT. Okay, so let's look at the purpose and design goals that we set ourselves at the start of the project. The purpose was to encourage more people to become robot builders, with the goals to provide a robot platform we can build with a first-time builder. It requires only basic hand tools and soldering equipment and is using parts that you can easily get and are common materials. We've also striven to keep the cost as low as possible as we've gone through. The robot should be capable of performing line following, wall following, and drag racing, and that would also cover the whole gamut of competitions that are run by the IET. And finally, the robot should be capable of being enhanced by the people that build it. So it'll provide a platform, but you could build on that platform and make the robot better. Have a look at what we've come up with in terms of the hardware. Okay, so here is the main board of the UKMARSBOT. You'll see that the PCB itself is the chassis. Its size is actually limited by the size of the freeware version of some of the PCB layout software, but this isn't really an issue for us because we want to keep this as small as we can, in particular for operating inside a maze. There are no SMD parts on this board. You'll see that everything on the board here is all through hole and no surface mount devices, keeping soldering as simple as possible. We're using a Nano microcontroller on here, again very readily available, very capable, low cost, and there are plenty of libraries for the software and also training material for this device available to builders. So a very common device and very simple to use. We're using N20 motors, again, very standard motors, gear motors, where the gearbox ratios are available in many choices. So the dynamics of the mouse can be changed just by changing the gearbox ratios to suit your application. The wheels actually can be mounted inboard in these slots here for smaller wheels, but if you need bigger wheels for maybe more speed or rougher terrain, then the motors can be mounted in such a way as that the wheels come outside the chassis and you can go ahead with those larger wheels. There is accommodation here to install the Hall effect Polludo encoders to give distance measurement through the odometry there. We also have, again, a very readily available but very efficient motor bridge controller based on the SparkFun. Again, as a module with through-hole soldering for simplicity. We've avoided the use of expensive connectors on the board and stuck with 0.1 inch headers, which you can obviously achieve very reasonably. Using a PP3 battery up here, the PP3 battery form is available in many formats and many rechargeable forms of that battery available for use on the robot. And finally, tucked away in here is actually underneath the Arduino in practice are quad XOR gates, and I will talk about those a little bit more in a moment. So let's have a look at some of the circuits that are actually on this board. So this is the entire circuit for the UKMARSBot. It includes all the elements that we have for the motherboard. And what I'm going to do now is just break down a few of those to speak about those in a bit more detail. And we'll start with the Arduino Nano. So here is the Arduino Nano. It's a nice device, but it only has 30 pins. So pins are at a premium. So that's been one of the major design features of this robot, is trying to get as much as we can out of the pins that are available from this device. So I/O typically would have more pins on a robot, and we've had to be pretty inventive about some of the things we've done. So you can see all the pins here are actually in use. We haven't left any untouched. So let's start to talk about some of the ways that we've had to be inventive to reduce the number of pins that we require to make a working robot. And this first circuit here is actually a relay ladder that replaces 5 different inputs, and we've actually put all of those inputs onto one pin by reading it as analog. So by the different analog signal that will appear by closing these different switches, we can actually decode that back to the digital inputs using software reading the analog pin. So that's one thing we've had to do to cut down the number of pins that we've been using. And we've got this extra push button here, which is switch 2. Works fine, but you need to be aware, obviously, that you cannot read all of these dip switches while that push button is pressed, because the push button is pulling that input up to 5 volts VCC. What else have we had to do around getting the number of pins down? Well, we've simplified the motor control. We have a very good motor controller in this Toshiba chip, but it does require quite a lot of inputs in its native form because you have 2 directional bits for each motor and a PWM signal delivered to the motor to control the power of the motor. And in addition to that, there is a standby capability. You can set this chip into standby. So by the time you finish with 2 motors needing 3 pins each and 1 pin for standby, you're up to 7 pins. And we don't have that number of pins available. So we've simplified our control, first of all, by removing the standby and having the motor controller permanently enabled by taking that pin high. But then also in direction, we have a single bit, which is either high for one direction or low for the other direction. And this is where our XOR gates come in. So by taking that 1 bit high or low, we can provide the combination of 2 bits, 1 high, 1 low, and always 1 high, 1 low to control the motor controller in the way it wants to be controlled, but by us only using 1 pin. We have used the XOR gates for other things because we needed to install the XOR gates. We put quad XOR on there. We're only using 2 for the motor control. We're actually using the other 2 to improve the resolution of the quadrature encoders on the back of the motors. And there's a very good materials about this on our website, and I refer you to those because they are good reading and probably beyond the scope of this initial presentation. So we've looked at the main board and the motherboard, but we've also provided with UKMARSBOT some basic starter sensor boards so that you can sense a line or that you can sense walls in a maze environment. And again, we followed the same principles. All through hole parts, no SMD, all on standard headers, excuse me, but the builder can choose the devices that they want to install. There are a few suggestions in the schematics, and also they've appeared on the screen on the boards here, but you can choose whichever devices you want to put on there and the resistor values that go with them. And actually there is here is the 14-pin connector that connects back to the main board of the robot. That's what connects the sensor boards into the main robot. And builders can do what they will in terms of making a board that connects via this 14-pin connector. You'll see that our line board, our basic line board, doesn't actually use all 14 of those connectors. I think it's down to 10 because those are all the connections that we need. So one option for using the UKMARSBOT is to use it as a teaching platform. This has been done by Birmingham City University, who leave the task of designing and building a line following sensor board as part of the work set for students. So you can build your own, or you can start with one of ours. The main thing being keeping to the interface and then making amendments to it as you want to. I have mentioned, I will just touch on this, I have mentioned, you will see other materials on this, that on the basic line sensor board, we have built it in a way that if you need to extend these wings out to one side, you can do fairly readily, and there is some materials available to tell you how to do that, again, on our website. So, moving on to the schematic for the basic line sensor board, we can have a quick look at this here. So we have the main connected to the motherboard. That's where all our I/O is coming in, and also power for the board. We have put a couple of indicator LEDs on the board, which is always useful, so you can switch those on and off to see what you're doing. Some suggested devices here, but you can use what you want. Again, phototransistors for detecting either side of the line, the start finish, and the radius markers, and emitter LEDs. Again, these are entirely your choice. We will talk about those a little bit more. Emitters can either be switched on permanently by using this link, or you can install a transistor here, Q1, to pulse those emitters. So, in practice, they look like when they've been built. Over here, we have a couple of pictures of the robot built with its wall-following sensor board installed through that 14-pin connector. And over here, we have one that's in line follower format with the line following board installed again through that 14-pin connector there. This particular line follower has extended the sides of the sensors to read the markers more reliably, and this particular build has had a Bluetooth module installed onto the mouse to allow some remote control of starting and stopping and logging data. If you're going to build a UKMARSBot, it's going to end up looking something like this, but the next slide is probably the most important slide of the presentation for you. So here are the links to where you can get more information and more help. There's a GitHub build guide. It's here on the wiki. It absolutely takes you through step by step. It tells you what tools you need and how to approach building not only the main board, but also how to build the sensor boards as well. So there's loads of material there to help you through the build of the robot. If you're wanting to get hold of the artifacts that make the robot, if you wanted to get hold of the sensor board and change the sensor board to be your design, then all of that material is available again on our GitHub, and you can download it. It's open source. It's there if you want to take it, or if you want to order your own copies of the board. On a wider level, the UKMARS website has all the details about the events we're running, when they are, how to register, quite a lot of descriptions of robots and lots of articles that can help you on your way to getting things built. So if you're building a robot, do go to these sources and see what's there. You'll probably save yourself quite a lot of time. Based on my experience, here's a few thoughts on the kind of things that you need to think about when you're going to build a UKMARSBot, and we're starting really with the hardware. On the main board and the rolling chassis, use the build guide on the GitHub wiki. It's fantastic. It will take you through, and you will be able to follow that through really well. If you're building your own designed sensor boards, the first place to go is to think about the contest you're going to enter and read the rules. There will be lots of detail in there about spacing and distances and what you have to do and where your robot has to be. So take that into account when you're building your sensor boards. Look at your emitter and sensor geometry. Think about either the walls or the line or whatever it is you're trying to sense, and figure out the best way that you're going to be able to get a good signal back on those. But also think really early on about the mounting and mechanical fits of your sensors. If your sensors aren't securely fixed, then you're just not going to get good readings on those sensors. And then you can think about the illumination strategy on your sensors. Are you going to use fixed illumination? We saw that link that allows you to do that. Or are you going to use pulsed illumination? Pulsed illumination is generally better for eliminating the effects of background or ambient light. Fixed illumination is clearly simpler. And whatever you do before you start soldering bits onto your boards, prototype your emitters and your sensors and check out the resistor values that you think you're going to want to use. We're going to talk a little bit more about that in a moment, but get your values sorted out on the bench or on the table using breadboard before you commit to soldering devices that you might regret and then have to unsolder again at some point in the future. And finally, if you're thinking about emitters and it's your first time build or early build, then we would recommend that you use visual light as your emitters. You can see what's going on. You can see when your emitters are actually working. You can see where they're shining. And also, it's really important from a safety point of view. If you're thinking of using infrared, you need to be sure that you're not going to be sending out damaging levels of radiation that could hurt your eyes. So be careful if you're thinking about using infrared. It's certainly more than possible to build these robots with visual light, and it's much easier to see what's going on. Talked about prototyping sensors before you put them on. And this is a little bit of a jumble on my kitchen table, but the point here is that you can build this robot either in a lab or you can build it at home, and you don't need a lot of stuff to get it to work. So this rig here, I'm just going to show you what I have. I'm just going to turn on the pointer here. So over here, those two clear devices there, one is a LED and the other is a phototransistor. So that's basically a sensor pair of emitter and receiver. And I have positioned a board with a white line, similar to the white line that I'm going to want to follow as a line follower, on a piece of blackboard. So this is simulating a line following track on a sensor. So I would rotate that to be facing down directly above those two sensors when I wanted to do tests. And spaced off by any suitable device that can get you the height that you think will be the right height of your robot as it runs along the line. The rest of all these gubbins is about firing the robot, the LED, because I'm using a pulse technique rather than a continuously on technique. And over here is the Arduino plugged into the breadboard, running a test program so that I can check out what's going on with the line. So to test it out, I would move this board so the sensors were on the line to being partially on the line to being off the line to see what would happen. Now, if you're at college or school or even a keen hobbyist, you may well have an oscilloscope or a picoscope or a bitscope to help you see what's going on. But these devices aren't essential. You can actually get the information you need about your sensors working by a simple program in the Arduino, sending values back to the serial monitor that you can read off and see what values are coming back from your phototransistor or your sensing device under different scenarios. It is nice to have the oscilloscope if you've got it, but it's not essential. So these two traces over here are showing you what I was seeing coming back from this sensor pair over here. So the green line is actually the low side of the LED. So this is the LED when it's switching on. The low side goes down. And the yellow line is the output from the phototransistor. So this top plot here is where my sensors are slightly off the line. So you can see there's the phototransistor firing, and here is, here's the LED firing, and here's the phototransistor's response. while the sensors are slightly off the line. And this plot down here is actually what it looks like when I'm directly over the line, which is what I want to see. So I'm getting pretty well a nice big displacement when I'm over the line coming out of the phototransistor. And then when I'm moving off the line, I'm getting a gradual reduction in the phototransistor's reading. And the only other thing to pull out here, which you can see with an oscilloscope, and you can't see necessarily when you're doing your own, doing this just by outputting values to the serial monitor on the Arduino, is you can see the time delay response between the LED switching on and the phototransistor actually reaching its stable value. So you know how long you need to wait between switching on the LED and reading the phototransistor. So you get them all working on here before you start soldering them into the boards. Let's talk a little bit now about software. Well, the Arduino has masses of libraries, more libraries than you can shake a stick at, and loads of examples and tutorials. And the big advice here is to keep it simple. Just keep it simple. Use stuff if it's useful, but primarily don't get overcomplicated with what you're trying to do. Look at the sample code on the UKMARS GitHub. We have put sample code up there. It won't run you a wall follower or a line follower straight out of the box, but it will give you lots of ideas on how to use the hardware and also put things together. But whatever you do, make sure you understand what you've got in your robot. You will not be able to debug your robot and get it to do what you want it to do if you don't know how your software in there is working. So don't just copy loads of code from somewhere. You need to know how it's meant to work. As a starter, here is a basic block diagram for a simple line follower. And I'll just walk you through the elements of this simple line follower. Two main threads to the software. Most of the work goes on over here. You want to go around checking things, and your control loop will sit driven from a timer interrupt typically. The one I use, and I think pretty well everyone uses on UKMARSBots, is a 2 millisecond timer interrupt. So you'll get a timer interrupt which will start your control loop software running. And while you're in that control loop, you'll be sampling your sensors, so you'll be looking to see what's going on. And based on what you've seen from those sensors, you'll decide where you are. Are you have you started, or are you finishing, for example, from the start-finish markers, or is there a change of radius coming up because you've seen a radius marker? You'll look at the error. That'll be the difference between what you think you should be seeing from the line and what you are seeing. And based on the error and where you are in terms of what state, you'll make adjustments to the power to the two motors to try and improve matters. So most of the work is going on here. The foreground program is really constrained to initializing the robot, making sure everything's set up right and ready to go, and also the human interface. So reading those dip switches and responding to the push button to say start, or maybe if you've had to pick it up after crashing, the push button may well tell you to stop. So those are the elements that make up a simple line follower. We can actually build on that simple line follower, which all those elements are still in here, but we've added a few extra things into this software to make a slightly more complex line follower. The main thing we've added here is we've actually added encoders on the motors, so we have some idea of distance. So as well as a timer interrupt in your loop, there will be encoders on the back of the motors driving interrupts from which you can calculate distances. And because your control loop is on a fixed time base, typically 2 milliseconds, because of that and knowing what distance is, you can calculate your speed and your angular velocity. So you now can enhance this control of the motors, not just to include what's going on with the line and what state the mouse is in, but also using the speed and angular velocity of the robot to end up with your final adjustment to the two motors. So this is adding odometry over here to the control of the robot. The other thing you can do if you're going to enhance this is, because you know about distance now through your odometry, you can start to memorize the line by, in the case of exploring the line, writing the maneuvers, or if you're getting onto a faster run, reading the maneuvers in advance so you actually know what your robot's going to have to do. These are all things that can either be added or not added, and you can do this in a very progressive manner. Finally, you can add an extra length to the foreground program. We've talked about it previously. It's not really doing very much. It's waiting for you to press buttons or flick switches. So you can actually give it some work to do by logging some data, maybe from your sensors, that you can look at later on and see what's going on. So that's the more complicated block diagram for the software of a line follower. So we've been fairly exhaustive now in looking at things, and you may want to be assured that there is something about this robot that makes it worthwhile and it can actually work. So I'm going to show you just a brief clip now of a build of a UKMARS robot going around the line follower course that was actually the course used in the 2019 UK competition at Birmingham City University. So here is the robot. You can see that it runs using visual light, and this is the Explore run, so it's running without any previous knowledge. So from that run that we saw going there, we can extract a little bit more information from it. So I apologise for the background noise on that recording. It was a pretty noisy environment. So what I'm showing you here is some data. Remember I talked about doing some data logging maybe in your foreground program, rather than just be sitting there waiting for the next timer interrupt to come along. And what we have on here are a couple of plots. This first plot here is looking at the start-finish sensors. So red is the start-finish sensor, and green is the radius sensors. They are the markers that are on the course before every change of radius, so before every curve or coming out of the curve into a straight, to see just what this robot is seeing. And you can see some fairly nice, clean markers here. And the last thing you see, of course, is the finish marker. You don't see the start marker because the logging starts as the robot starts. So we run along and then we see the finish marker. And this is all fairly encouraging, but there's a couple around here that we might want to look at, because are those markers or is that noise or something going on the track? And I think the robot that you saw running there didn't have the extenders on it that I've talked about before, and as a result, things like this occur, and they can be removed by extending those sensors. The second plot up here is actually what the sensor on either side of the course line are seeing, and you can see they're trying to keep a pretty constant difference between those two, because there is a slight difference on the robot here, by keeping that, keeping the line in the middle, so the gap between those two, the blue and the grey line, stays pretty constant throughout. So we can be pretty happy with the robot that we just saw going around there, seeing markers, and it also pretty much staying tidily on the line. So I think I said earlier on that this was probably the most useful page of the presentation, and that's why I'm ending and back up on it. So thank you very much indeed for watching this presentation. I do hope it's caused some interest for you. Here are all the resources that you can use, and maybe if you want to have a go, why not have a think about joining UKMARS as well. One of the features of UKMARS membership is that a member can apply for a free set of boards, the motherboard and a basic line board and a basic maze board. So thanks again for listening, and hope to see you soon.